ekranımı
Okay, hello everyone. Welcome to this new episode of our EE590. Today we have three presenters. Ayşe Kübra Çevik, Yusuf Karabacakoğlu, and Nuri Baran Ayata. So let's start by hearing from Ayşe Kübra now.
Hello everyone, my name is Ayşe Kübra Çevik and today I will be presenting about multimode antenna concept at 5G millimeter wave frequency band. Here you can see my outline. Firstly, I will be talking about the difference between two frequency bands used in 5G communications, which are 6 GHz and millimeter wave frequency bands. Then I will give a brief overview about beamforming and phased arrays. In the last part of the presentation, I will talk about multimode antennas. And here you can see the evolution of 5G. In 1980s, there was analog communications and most of us were not around. In 1990s, text messaging started. In 2000s, mobile and wireless internet communication became available. In 2010, cloud, IP, and mobile broadband became accessible. And now with 5G, unlimited data capacity is expected to be achieved. Fifth generation cellular wireless is now succeeding 4G LTE networks that have been in service since 2010. Cellular phone companies began deploying 5G worldwide in 2019, and it promises to connect everyone and everything. High-speed connectivity, ultra-low latency, high reliability, large network capacity, consistent user experience are some of many advantages of 5G. After giving a brief overview about 5G, we can now start discussing differences between sub-6 GHz and millimeter wave frequency bands. Sub-6 GHz band covers middle and low frequency bands. However, millimeter wave band covers 4 GHz to 40 GHz frequency band. Consequently, it has smaller wavelengths. And high-frequency signals attenuate faster and they are suitable for traveling shorter distances. Also, reflection from obstacles is another downside of high-frequency signals. So, how can we overcome these unfortunate high-frequency properties? First, in 5G, there are low-power cellular access nodes called small cells. They are basically miniature base stations and their ranges from 10 meters to several kilometers. Secondly, multiple input, multiple output antennas can be used to increase signal-to-noise ratio and the channel capacity. And the third solution is using phased arrays to form beams. And this brings us to the second part of this presentation, which is beamforming and phased arrays. It is another approach to increase the signal strength, and it utilizes multiple antennas to receive or transmit strong focus signals. This animation shows how a phased array works. Antenna array consists of elements that are powered by a transmitter. Feed current of each antenna passes through a phase shifter, and phase shifters delay the waves progressively. Each antenna element has a spherical wavefront. After superposition, the spherical wavefronts are constructively summed up in a certain direction to create a beam. So, can we change the direction of the beam? Yes, it is possible to steer the beam direction electronically without physically moving the antenna. The phase shift added by phase shifters can be controlled by a computer system. By adjusting the progressive phase shift amount, it is possible to redirect the beam. When beamforming used with massive MIMO in small cells, fast and reliable communication can be achieved. However, implementation of massive MIMO and phased arrays requires a large number of antennas. And this makes the implementation of miniature base stations more expensive compared to the conventional radio units. Also, design becomes more complex and cooling becomes a major problem as the number of antennas increases. And this brings us to the last part of this presentation, which is multimode antennas. A multimode antenna has multiple ports that can excite different characteristic modes independently. Each mode gives a different radiation pattern. In other words, a single antenna can act as a multiple antennas with different radiation patterns. And here in the figure, you can see 3D radiation pattern of a multimode antenna with 4 ports for 4 different modes. And in this figure, you can see the usage of a multimode antenna on a MIMO system. This is a 2x2 MIMO system, and it is synthesized out of 4 modes of a multimode antenna. So instead of using 4 antennas, 1 antenna is sufficient. My thesis will be about designing a multimode patch antenna working at 24.25 gigahertz to 28.5 gigahertz frequency band. This frequency band has been chosen since it's planned to be used for the 5G millimeter wave base stations in Turkey. Within the scope of the thesis, only 1 patch antenna will be designed. However, this single patch is planned to be a part of a very large phase array to use beamforming and massive MIMO. And I'm concluding my presentation with the hope that one day this vision may come true. Thank you for your attention.
Thank you, Kübra. So any comments on Kübra's presentation?
I love the finishing sentence.
Yeah, thank you.
I think you had a very nice upbeat attitude. I think finally we're getting there, right? Everybody is now understanding what is expected, by the audience from the speaker, and you have successfully catered to that, Kübra. You had energy, you had a positive attitude, nice slides. I don't think I have anything negative to say.
Thank you.
But other people may have recognized things that I didn't catch. So please go ahead if you have any comments to tell Kübra so that she could possibly improve. No? Okay, then let's hear it from Yusuf now.
Can you see my screen? Hello, everyone. I'm Yusuf Karabacakoğlu. I'm a master's student in Middle East Technical University. I'm working with Gökhan Güvensen. My thesis topic is nonlinear signal processing for physical layer in 5G. First, I will talk about evolution of 5G and its capabilities. Then, I will discuss a challenge in 5G, nonlinearity. And then finish my talk with discussing handling the nonlinearity. In 1980s, 1G emerged. There is only voice communication, and it has speeds up to 2.4 kilobits per second. In 1990s, text message is also added, and the speed is 64 kilobits per second. In 2000s, 3G emerged. With this, there is a mobile broadband, and it has speeds up to 2 megabits per second. In 2010s, 4G emerged. With this, video communication is added to the communication scheme, and it has speeds up to 100 megabits per second. Currently, 5G is emerging. It offers Internet of Things, high-speed internet, Ultra HD, 3D video, and many more things. And also it offers speeds up to 1 gigabits per second. It's great. Speed increase is due to the using massive multiple input, multiple output antenna. It's one of the key technologies. It's basically, instead of using one antenna, use many antennas so that more data can be transmitted. The picture in the left shows a base station deployed with massive MIMO. There are hundreds of antennas, and it can serve 10 users at the same time. If there only be one antenna, it can serve only to one user at a time. So we can say that there is approximately 10 times increase in the data rate. The picture in the right shows a real implementation of a MMC MIMO antenna array, but currently they are around 64 antenna array elements. But in the future, the expected number would be much more. But in 4G, expensive high-quality components and a powerful antenna is used. But scaling it to many antennas won't be practical for 5G. We need cheaper components so that the overall costs can be bearable. But cheaper components come with a cost. They cause nonlinear distortion, which degrades the system performance. For example, 2-bit quantization is much cheaper than 8-bit quantization in terms of cost and power consumption. But in this picture, you can see that 8-bit quantization is like the original sine wave, but 2-bit quantized version is much different. And if that distortion is not handled, instead of a 10 times increase in the data rate, we would have much lower increase. And that brings us to our last topic, handling the nonlinearity. In the literature, typically precoders are used. Idea behind it is that by shaping the signal to a specific form before it passes through nonlinear components, distortion can be lowered. There are two main classes of such precoders, linear ones and nonlinear ones. Nonlinear precoders have better performance, but they are more complex to implement than the linear ones. Signals represented as vectors for simplicity. For example, X is a vector consisting of capital N elements, and each element can be thought of as a one user data symbol. W represents a matrix. Linear precoders are in the form Y equals Wx. Typical examples are zero forcing and maximum ratio transmission. The idea behind them is that by using the channel information, design the W such that the signal power is maximized. They are easy to implement, but they offer poor performance compared to nonlinear ones because they ignore the nonlinear distortion discussed before. Nonlinear precoders, on the other hand, uses a general form, that is y equals function of x. And it is hard to find such functions. But if it would be found, they offer better performance. Current nonlinear precoders in the literature some of them are based on basis function representation. For example, power series expansion. But basis function may not be able to fully span the distortion term. So there may be left distortion. Some methods are based on lookup tables, which is similar to a basis function idea. By using a predefined mapping, they try to minimize the distortion. Some of them are MMSE-based practical algorithms. The original MMSE consists of a huge matrix inversion, but that matrix inversion is costly, computationally costly. So they resort to more practical solutions by making some assumptions. Overall, all of the solutions here made some assumptions to obtain a practical solution. But in real life, those assumptions may not be met, and there would be some problems. Our approach is models the distortion Q with Buscanc decomposition. And Buscanc decomposition tells that any nonlinear function can be composed of a linear term and a distortion term. Bx here is the linear term of x, and n is the distortion. And also, x and n are uncorrelated. And we estimate n with our distortion model. Then we put x in a format such that effectively we subtract n from y, so that we only left with the linear term. which means nonlinear distortion is minimized. If our design can estimate N accurately, we expect to see performance increase compared to other methods in the literature. Currently, we are working on our distortion model. Hopefully, our work would contribute to development of 5G and future generations, so that the human experience improves. Thank you for your attention.
Very nice, Yusuf. Wow, today I'm really impressed by our speakers. Yusuf, particularly your choice of background is very nice. And given that your work is theoretical, there are books behind you. This is, you know, a very nice, consistent choice of background for your material.
Thank you.
You know, on the other hand, Kübra is a little bit more practical, perhaps. Her work, it's a little bit more experimental, perhaps. And I mean, I admire Kübra's background. I've said that several times so far, but I think, you know, Yusuf's talk has shown us that the consistency between our choice of background and our material is a useful tool in putting the audience in the right set of mind for listening to our material, right? I mean, we never thought about this before. My notes do not cover this because we are only we have only entered the era of online talks recently, and the concept of a virtual background gives us extra flexibility. We can create the environment that we want. In fact, if it serves your purpose, you might want to play some video in the background, you know, depending on your talk material. So one thing, Yusuf, that I might add in terms of constructive criticism to your talk is I think you could make use of a pointer because you're talking about an equation, for example, and you're talking about eliminating something or you know, estimating another thing, etc. It would help if you pointed to the symbol or to the equation that you're talking about, because yours is not just something that you can, you know, people can verbally understand. You need to refer to equations and symbols. Yes. So point to them. Okay. All right. So I think it's time to hear Nuri Baran if he's ready. Nuri Baran Ayana, can you hear us? What to do about this? Let's wait a little bit, and in the meantime, I can record the attendance for today. So we have Tutku is here. Yes.
I'm here.
Muhammed Akbulut is. Muhammed Akbulut, are you here? Huh? Yes, you're here. Bushra is here.
Yes, I'm here.
Ali Furkan Aslan. Yes. Nuri Baranayana is, he appears to be here, but we cannot hear from him. Talha Çalış.
I am here, Nuri Baranayana. So
okay, Nuri.
Sorry.
Welcome. Okay, we were waiting for you. Well, while you recover your breath, maybe we can continue with the attendance recording business. So Talha Çalış is not here today? No? Sinan Çimen,
Buradayım hocam.
Güner Can Dündar, not here today. Oğuz Onur Güngör, Mehmet Gürtekin, Osman Furkan Kar. Yes, he's here.
Buradayım hocam.
So Mehmet Gürtekin is not here, right? Yusuf Karabacakoğlu is here. Of course. Metehan, yes, here.
Buradayım hocam.
Tuğberk is here. Metecan Kaya. Metecan Kaya. Yes. Mustafa Kılınç, yes. Kemal Parlak Tuna. Kemal Parlak Tuna, yes. Yeah, if you just wave, I'm not going to notice probably. you need to speak. Fatih Serdar Sağlam, is he here? So Talha Çalış is in the waiting room. Let's admit him. Talha Çalış. He's arrived late. Okay. Fatih Serdar Sağlam. Nope. Furkan Şık.
Here.
Okay. Onur Yılmaz is here. Yes. Okay, so we're done. Now we can hear from Nuri Baran.
Sorry, wait a second. I believe all you can see my screen, right?
Yes.
Okay. Hello, everyone. I am Nuri Baranayan. I'm a master student at Middle East Technical University and currently working on my master thesis with Professor Kemal Levlevicioğlu. Today, I'm going to mention about, this is just subtopic of my, it must be subtopic of my research thesis, which is sensor management by using multi-arm bandits. So this is the content of my presentation. First, I'm just going to give a brief introduction by taking what, why, and how questions into the account about sensor management. Then next, I will explain my problem definition, and I will reveal my motivation behind this work. Later on, I will touch on literature review with little. Then I will pass the proposed method and what's multi-armed bandits and how I am planning to model multi-armed bandit formulation on my problem. And I will finish my presentation with outcome and evaluation part. So what is sensor management? It's a general statement of sensor management is used to manage and coordinate sensor usage to accomplish specific objective. This objective changes according to the working field. But specifically, sensor management takes its place where the sensor integration and coordination is required. In defense industry, so this is where I want to work on. The ultimate goal is optimize the overall performance of tracking and classification system. This figure is just a closed loop sensor management model. There are just a whole sensor management closed loop model includes different functionalities. This you can see S1, S2, and S3 in the left. On the left are the sensors. This sensor selector part where corresponds to the sensor management part. So physical configuration, beam steering, and waveform selection. These are different talents. Sensor management will fix and change and optimize. What sensor management optimizes these and different functionalities. Why do we need sensor management? It is mostly used reducing the workload of the operators in different fields. Where the operator takes its place, sensor management is used. And also another thing is prioritizing and scheduling sensor service requests, maximizing the effectiveness of the overall data fusion system. These are the different things where sensor management is used. And these are the some fields I have chosen according to my interest. multi-target tracking systems, and command control and communication system where I work on, and mobile robot system and modern tactical aircraft systems include sensor management in these systems. How to solve sensor management? Sensor management can be solved via various algorithms and formulation approaches to resolve scheduling and decision-making objectives. It has a wide usage area, but it's basically split into two basic fields. The first is scheduling techniques and decision-making techniques. These are some algorithms. The one I'm going to mention, multi-arm bandit, is not included. Maybe it is why multi-arm bandit is exciting for me on this field. It does not be used very generally. My problem is it possible to achieve high quality target tracking and restrained radar risk level in a multiple radar, multiple target systems with sensor management? You can see here there are two radars with their coverage areas and two targets. While these targets moves on, they go to infinity. It's not important where they end up. If these two radars work all the time, we have better optimal aircraft, optimal air picture, because we all the information. But while all the radars makes a radiation, the intruders, these targets, can know their location. So this means if they all the time makes radiation, their risk level increases. So I have to provide sustainable and high quality target tracking, and at the same time, I am planning to constraining risk level 2. So this is why sensor management is required in this problem. This is just a basic literature review. I didn't go into too details, but the one I have found has been used hidden Markov model for resource management algorithm, and another one sensor management was formalized with partial observable micro-observation process, and Lagrangian relaxation was used to reduce computational load. And another work, particle filter was used for both target tracking and resource management. I can just summarize this my literature review as all the works in one way or another is optimal, but all the researchers have emphasized that computation load is a big problem. So this is why multi-arm bandit is important. It dramatically reduces the computational load. So what is the multi-arm bandit? It has emerged from the casinos, actually. These are slot machines in casinos. The gambler want to create a strategy in a way to choose one slot machine and at this specific time. So there are n slot machines, and gambler choose one of them at in the period. So this is the decision variable. It takes 1 and 0. This means you choose only one arm. This means only one slot machine. So others remain frozen. Also, I want to emphasize that multi-arm bandit has a lot of types. So this one is called a Markovian multi-armed bandit because one arm is used while others remain frozen. So the one is selected, for the one selected, state vector is updated, and others, as you can see, just their state vector, the situation remains the same, remains frozen. And we calculate the reward. The goal of the multi-arm bandit is maximize the cumulative reward in a specific time. This T changes, of course, if you wanna, for example, for gambling, if you want to play 10 times, this multi-arm bandit is aimed to maximize the cumulative reward for that time and place. So jitters index is the solution. This means this helps us to choose which arm to choose in a specific time. So we calculate the jitters index and we choose the arm with highest jitters index value. After the brief introduction to multi-arm bandit, this is my modeling algorithm strategy. This is the one I have planned. This is not in the version with too detailed version. I am taking as an input target quality and radar risk assessment. Of course, this is a whole different story. It must be too detailed. But I just give this one as an algorithm input, and I calculate distance index for specific radar. I have chosen, of course, I have written this, but as I said before, only one arm is chosen. This means only one radar is chosen in a specific time, and it's stated, updated, and we calculate the distance index, and we choose the radar with highest distance index and activate it, and others are deactivated. This means remain frozen. Before I finish my presentation, this is now my evaluation part. For this topic, sensor management is used in order to provide good tracking quality and constrained risk level of radars. And in literature review part, various researchers have been worked on this problem. Different applications have provided with optimality, but they all have something in common. The all optimal works has the problem of curse of dimensionality. So I prefer multi-armed banded model to optimize the sensor management with tolerable computational load. Thank you for your attention and listening.
Thank you, Nuri Baran. I think you came to the talk in a hurry.
Yeah.
I think that adversely affected your presentation a little bit. But that's also one of the factors. I mean, maybe you had factors that you know were out of your control today. I don't know, but in general, it is really important to allow yourself enough time before the presentation to be ready and relaxed and have everything working in order. Now, in your talk, you used some references in the literature review part. If you could go back to that slide.
Of course.
I would recommend that when you're giving your references, omit all of these page numbers, issue numbers, etc. You know, so give the author names. You don't even need a label like 1, 2, 3. You know, don't use this reference structure that you would use in a paper. The first important work is by Whittenby and Krishnamurti, and it appeared in 2006. You could also give, if you want, IEEE transactions on aerospace and electronic systems, if you want. But what's important is the authors, the year. Okay, we don't need the paper title. We're not going to read that. All right, David Castagno. Yeah, it's good to know that you have followed, you know, you have explored what's in the literature and listed 3 major milestones, if you want, from 1997 to 2002, 2006, separated 4 or 5 years apart, and now we're in 2021. It's you. You know, this is interesting. Maybe you could also put this in a timeline. I mean, here going from 2006 back to 97 maybe is not the best idea. Maybe you would want to make them chronological. All right. So other than that, whenever people mention the multi-arm bandit problem, they use the word optimal, but these indices, Gittins index, etc., it's hard to prove optimality. Okay, so just keep this in mind. I mean, choosing the arm that has the Gittins index may work well. It is hard to prove for many problems that it solves the multi-arm bandit problem optimally. But if you have that proof, of course.
I don't have, but as far as I read, they have. I don't know, but it was written just.
Excuse me?
It was written optimally, so I have always used this word.
Right. If you have, if you believe it, if you're referring to a theorem that's already available somewhere, it's best to just quickly reference it. I don't know, Castagno 97. for example. Other than that, you could use being a little bit more prepared in terms of the text of your talk. And today you were rushing, so I'm not going to be very harsh on you. You didn't have a closing sentence. You said so you said thank you for your time or something. Okay, other than that, very nice though. I mean, you were engaged, you made us engaged in the talk, you were energetic. So nice use of slides, etc.
Right.
What kind of question mark is this? What is this font?
I just used the Meta format. I don't know.
Really? Is that the question?
I didn't change it.
Wow.
Yes, they have this one.
This is very strange.
Yeah.
Anyway. Okay, everyone. So for next week, December 6th, December 7th, I believe we have 6 people. So we're planning for a longer session next week and then the week after. For today, I think we're done. I will be posting this recording on the ODTÜ class page, and you could take a look if you want, or if you don't, if you already remember, if you already took notes, just write in a few lines of comments for your classmates. And with this, I wish you a happy rest of your week.
Thank you.
Bye-bye.
Bye-bye.